Hello, I'm Malcolm Doring, and today I'm going to talk about our work in progress on learning social robot behaviors for interacting with staff and customers. We'll use a data-driven imitation learning approach, which consists of first doing human-human interaction data collection with a passive sensor network in some target domain, like in a camera shop with interactions between a customer and a shopkeeper. Then various machine learning algorithms are applied, such as clustering to extract the high-level meaningful behaviors from the raw data, and classification to map from the interaction state to a robot action. Then the learned behaviors are used to automate a robot to take the place of the target human, such as the shopkeeper here. The advantage of the imitation learning approach is that no hand coding of interaction behaviors is required. The designer does not have to anticipate all the ways the customers will behave, and also the designer does not have to be an expert in the application domain. There's also no data annotation required, which is good because this is expensive and time-consuming, and the robot learns from noisy sensor data, yielding robust interaction logic. We've looked at many variations of data-driven imitation learning to solve different problems in human-robot interaction. For example, my colleagues have looked at learning proactive shopkeeper behaviors, and we've looked at learning human interpretable interaction rules that can be modified or verified by a designer. We've looked at learning a memory model of customer behavior to remember the customer's preferences and act based on those. We've looked at a curiosity-based online learning mechanism to allow a imitation learning system to learn about individual customer differences and customize its behavior based on that. We've done one-to-many interaction learning where a robot learns to interact with not just one customer, but many customers. And in our most recent work, we used imitation learning to adapt to periodically changing products based on the contents of a product information database. But all these previous works focus on robot interacting with only customers. And of course, robots will also have to interact with fellow human staff members. So we conducted interviews of people with retail experience to find a set of tasks and ways that staff interact among themselves. We found at least two representative types of interaction and coordination among staff. One is where multiple tasks are split among workers and done concurrently and independently, such as managing a register, stocking shelves, and helping customers. The interesting thing about these types of tasks is that the robot would need to know about other staff members' preferences, skills, and abilities to properly split up the tasks. And the second type of representative interaction is single tasks that require multiple workers to work together. For example, when getting a product for a customer from a restricted area where only one staff member has access. With these representative types of interaction in mind, we designed an interaction scenario that contains two shopkeepers and one customer. The shopkeepers are assigned multiple tasks like stocking shelves, managing the cash register, and customer service. There are restricted areas such as shelves behind the counter and a stock room, and staff are assigned different roles with different abilities, such as liking or disliking customer service, knowledge of products, and access to restricted areas. With this interaction scenario design, we can observe various interaction dynamics, such as staff asking other staff members with access to get a product, bringing customers to other staff members with more knowledge about a product, and trading off tasks when one staff member becomes busy with something else, for example, if a customer asks them a question. With these interaction scenarios in mind, the question becomes what type of learning architecture is necessary to learn the interaction behaviors. Specifically, we need something that can coordinate the human and robot staff members' actions. The solution that we've come up with is to 1, predict what the other human staff member will do, 2, take a coordinated action, and 3, if the human staff action prediction is wrong, then preemptively modify the robot's action. And the proposed neural network would look something like this. We have a human staff model that is fed into a human staff action prediction neural network, and both of those are fed into a robot action prediction neural network, which hopefully predicts a coordinated action. And remaining to be done is our data collection and evaluation of this architecture. Thank you for your attention, and if you are interested, please take a look at our paper and our other papers, and feel free to contact us if you have any questions.